Hello, everyone. Hi there. My name is Ravi Vakil, and I'm president-elect of the American Mathematical Society. Kirsten Wickelgren is a professor at Duke University. After her PhD at Stanford with Gunnar Carlson, she was a fellow of the American Institute of Mathematics at Harvard, then a professor at Georgia Tech, before moving to Duke in 2019. In 2023, she was selected a fellow of the American Mathematical Society, and she's a member of the K-Theory Foundation. Her research focuses mainly in homotopy theory and arithmetic geometry. She's made important contributions to the study of A1 homotopy theory to enhance classical results in enumerative geometry, which is a topic close to my heart, incorporating arithmetic insights. I'm honored to have known Kirsten since she was a PhD student at Stanford, and even at the start of graduate school, she had ferocious technical power and the ability and inclination to work with particularly abstract ideas, but that was notably combined with a willingness to get her hands dirty with examples and specific arguments. She would always want to know why things were true all the way down to the nuts and bolts. She would also not have any respect for disciplinary boundaries, following her interests across topology, number theory, algebra, and geometry. She taught me to think more broadly and not to be afraid. So I'm looking forward to hearing her now. Please join me in welcoming Professor Wickelgren.
Thank you so much for that very kind introduction and for the opportunity to speak here. It is an honor. I'd like to talk about arithmetic aspects of enumerative geometry. So enumerative geometry counts the number of algebrogeometric objects satisfying certain conditions. In fact, even the number of solutions to a degree n polynomial can be viewed as an example of this. So there are exactly n solutions in an algebraically closed field of a degree n polynomial. But if, say, those coefficients were in Q, some of those solutions, they might be in Z, they might be in Q, they might be in Q adjoin a square root of 3, they might be in R, Q adjoin I. And our goal in this talk is to record arithmetic information about the fields of definitions of those algebrogeometric objects, the fields and rings in which solutions are going to appear to our problems. And the tool that we're going to use is A1 homotopy theory of Morel and Voevodsky. So we're going to start by looking at the beautiful smooth cubic surface. And then let's talk about A1 homotopy theory. And then we'll talk about A1 enumerative geometry, this goal of talking about the arithmetic of the solutions, or we could call that quadratically enriched for reasons we'll discuss. So a cubic surface is the zero locus of a degree 3 polynomial. So here's the Clebsch cubic surface. And we've drawn it in R because we live in a real world. And we could also look at the solutions in C, and that'll make our counts more invariant. And we're really going to be interested in a cubic surface over any field, and we're going to view it as a scheme. And what that means is a way to view solutions to polynomials as a kind of space that can be thought about as considering all the solutions and all the K algebras. So there it is, a scheme over a field K. And again, since we're counting, it's good to compactify. So the whole room sits inside a compactification where there's a P2 at infinity. So let's consider X in P3. A celebrated theorem of Salmon and Cayley from the 19th century is that any smooth cubic surface contains exactly 27 lines. And here you can see the 27 lines. They're even real for this special cubic surface. However, over R, this is not true in general. So Schläfli in the 19th century, again, showed that there can be 3, 7, 15, or 27 lines over R. Over R, let's look at the geometry a little more closely. So Segre introduced the notion of hyperbolic and elliptic lines. So let's take a real line L on a cubic surface, and let's look at a map from the line to the space of all planes in P3 that takes a point to the tangent space of the cubic surface at the point. So that's a plane in P3, and it has to contain a line. So you can get P3 by projectivizing a 4-dimensional space, and the line is this 2-dimensional space. So you want to projectivize the quotient, so you're projectivizing a 2-dimensional space, so it's a P1. So all the hyperplanes containing L is a P1, so you get this map from P1 to P1 that takes P to the tangent space. So here we're going along, and there's P, and there's the tangent space. And then X intersect this tangent space has to be degree 3, so it has a line, and that's a degree 1 thing. We need 2 more degrees in this plane curve. So that's a degree 2 curve there. And so it's intersecting that line at 2 points, and both of these points have the tangent plane that's written there. So we get to see that this map is a double cover of P1. So it has a Galois group that's a Z mod 2, and let's let I from P1 to P1 be the involution that exchanges the 2 points with the same image under tau, the 2 points with the same tangent space. So it sends every point of the line to the other unique point with the same tangent space. So it's an involution. Let's stay over R. And then it's fixed points. They can either be 2 points with real coordinates, or they can be a complex conjugate pair of points. And in the first case, the line is called hyperbolic, and in the second, it's elliptic. So you can actually feel which line is which. So what happens is, let's put the surface back in the room, and let's put our pointer finger along the line and keep our palm on the tangent space of the surface, and then we move our hand along and make our palm follow. That's actually a whole frame, because you've got your pointer, keep your thumb along the tangent space, and you're normal. So you're really keeping track of a whole frame in the room. And so you can really do it here. So first, on the very left, our hand is like this, and then it goes in that middle region where there's that, here, I can point here. So here, now we're here, and then it moves back the other way, and we're back here, and we straightened out. It's hyperbolic if, as you're following the line, you straighten yourself back out. However, this one is elliptic, so we can do it again. We start here, and we go around, but then we keep going in the same direction, and we are all twisted up. And then we could do it again and untwist ourselves, thanks to the fundamental group of the orthogonal group. But that makes this line elliptic. This distinction is measuring something about how the tangent space is spinning around the line as you follow the line. We have this theorem of Salmon and Cayley that says there are 27 lines over the complex numbers. And let's think of this new theorem up here also as a count of lines over R. Now, it's not really a count because there's a minus there, but that is what's going to naturally arise in this talk. And this is a beautiful theorem. It sort of follows from tables of Segre, and Benedetti and Silhol are very gracious and say it's due to Segre. Maybe it's not quite clear that Segre noticed it, as a Koenig-Telemann point out. And then there's a lot of beautiful things to say about the cubic surface, so a lot of people, Finesh, Kharlamov, Solomon, and even more, have great things to say about this. But here is a count of real lines. For example, it shows that there are 3 real lines, and it's some sort of weighted count. And what we're going to be able to do is to do this over a field that's not R or C. Looking ahead, let's let that K general just means K a general field. And then a line, it has some equations that cut it out. Let's let K of L be the field generated by the coefficients in all of those equations. And then the fixed points of that same involution that we defined are defined over some quadratic extension of K of L. So it's K of L adjoin the square root of something. And in some joint work with Jesse Cass that I'd like to talk about, let's call that A the type of the line, and it's measuring how the tangent space spins. Okay. So to get there, let's take a detour and talk about the A1 homotopy theory that Morel and Vygotsky construct. So there's a stable A1 homotopy theory that accepts, there's a functor from smooth K-schemes, so they determine objects in this homotopy theory, or you could make it a category, a one category of the homotopy category, and a smooth K-scheme will be in there. But you can also stick topological spaces in there too, and so you'll have both. And then you freely allow yourself the ability to crush. You could crush the P2 at the boundary that's compactifying this room, and that's allowed, and you freely add these crushings, and then you lose some of the geometry of your schemes, so you put it back. You say that the ways that we glue, they were free at first, but now if we have an open cover, we can glue the open cover back to make the original scheme. So we do something called Gauss field localizing at Nisnevich covers, and then in the A1 versions, although you can modify this kind of construction to handle geometries that have to do with questions you're interested in, but for us, we're also going to want to make A1 contractible. So let's make, A1 equivalent to the point. So that's an unstable homotopy theory. And to talk about cohomology theories, which it's useful to stabilize. So this smashing argument there, it's like taking a product, but then crushing base points across other factors. And so we want to make it possible, this is a suspension by P1, we want to make it possible to desuspend. And then that constructs this SH, and that can be written very compactly. So here's the unstable A1 homotopy category. It can be viewed as these A1 invariant sheaves inside pre-sheaves of topological spaces on smooth schemes. And then the stable A1 homotopy theory we get by inverting P1. So why would we want to do this? The A1 homotopy theory is a natural place where a lot of cohomology theories that did great things for many branches of math live. So we have the Betty cohomology of the complex points of a variety over K when it's a subfield. And we can take L-adic cohomology, like say over an algebraically closed field, and then it gets this Galois action. We have K-theory and algebraic cobordism and motivic cohomology. We can add forms to K-theory, and all of these cohomology theories live in the stable A1 homotopy category. And in fact, the stable A1 homotopy category is precisely where any theory that's A1 invariant and has Meyer-Vietoris for Nisnevich covers, and has the P1 being invertible, that's where these all live. And then anything you prove in A1 homotopy theory about that immediately applies to all of those cohomology theories. And since you can crush and glue, you can build more cohomology theories out of very successful ones that you already have. So you get to move schemes around like silly putty and stretch them and do all sorts of very free things, even though solutions to polynomial equations have a lot of algebraic structure. And you get to build a lot of cohomology theories. That's something about this world. The flagship result in A1 homotopy theory is Vygotsky's proof of the Milnor and Bloch-Kato conjectures, but there are a lot of other wonderful applications to vector bundles, back to algebraic topology, and we could say a lot about this, but that's our motivation for making an A1 homotopy theory. We could even make a joke, because when you stick a scheme in here, you could call it a motive, and then it's also a motivation. Thank you. So for our purposes, let's talk about a beautiful calculation of Morel. So we built this world to accommodate cohomology theories that have certain Meyer-Via torus. And then it is a calculation that the degree map is not an integer. The degree of a map between manifolds, it counts the number of preimages of a point. The degree of a map from a circle to itself, that entirely encodes the homotopy classes of maps from a circle to itself, and we know that to be Z. That's a calculation. But after making this world, even for other reasons, the maps of the circle to itself are these spheres. The map of the sphere to itself is no longer Z. It's fundamentally arithmetic. So it's this Grothendieck-Witt group. And it's defined by taking bilinear forms over K. So a bilinear form is a quadratic polynomial in some number of variables called the rank, or it's a bilinear map on a vector space across itself, and symmetric means the form is the same. It corresponds to a symmetric matrix of non-zero determinant. And then group completing means we are allowed to subtract bilinear forms in a formal way. So that's the Grothendieck-Witt group. Over a field, we can always diagonalize forms. So we've got generators for this group that we'll denote with a bracket A. So these are on a one-dimensional vector space K, and the angle brackets A is the bilinear form from K cross K to K that takes xy to axy for A and K star. So for example, this 2 plus 3 is the class of the bilinear form whose Gram matrix is 2 and 3. To get a handle on this group, let's note that we can get an integer, so we'll be able to recover counts over C by passing to this rank. So the Grothendieck-Witt group maps to Z via the rank. We can send a bilinear form to the dimension of V over K. And to recover our real counts, it will turn out that we can use a signature or sign. So if K is inside R, then it's a theorem of Sylvester that any bilinear form can be diagonalized to have a bunch of ones and a bunch of negative ones. And you take the number of ones minus the number of negative ones. So this is a homomorphism of sending a positive number to 1, a negative number to -1. Morel's degree has this beautiful property that if you take the rank of his degree, you get the degree topologically of the C points. And if you take the signature, you get the topological degree of the R points. We're going to need one more piece of notation to state some theorems. So if we've got a finite separable field extension, then the sum of all the embeddings from L into the algebraic closure is this trace from Galois theory. And so this, this goes from L to K. Sorry, this is reversed. The trace is going to be from a bilinear form over L. So the trace or transfer will take a bilinear form over L to a bilinear form now over K. So V can also be viewed as a K vector space. And then we take this bilinear form F, and we compose with the trace from Galois theory, and we can take something from GW of L to GW of K. All right. So we've got some notation to talk about degrees in A1 homotopy theory. So let's go back to our goal of doing enumerative geometry with A1 homotopy theory. This was developed in joint work with Jesse Cass and independently by Mark Levine and with work by Mark Hoywa. And it's lucky to have contributions by Azuri and Bachman and Brazelton and Broering and Jaramillo Puentes and Markwig and McKean and Paul and Pajwani and Pauli and Pep and Lahanar, Srinivas and Vergiver, among others. And since we've set up the cubic surface, let's now take that theorem about the 27 lines and the 3 real lines, or the weighted count of 3 real lines, and say that we have a common theorem that generalizes these. So it says that if you take a smooth cubic surface over K, that the number of lines on that smooth cubic surface is the quadratic form that's diagonal with 15 ones on the diagonal and 12 minus ones on the diagonal. So there are 15 1 plus 12 bracket minus 1 lines on a smooth cubic surface over K. How are we counting them? It's a weighted sum over the lines, and then here's that type. It's recording something about how the tangent plane spins around the line, and then it's recording the field of definition, but that's invariant. And then if you apply the rank, we see that there are 27 lines over C, and applying the signature, we see that there are 3 lines over R. So I'd like to talk about putting arithmetic information into Gromov-Witten invariance. And to do this, let's first talk a little about what Gromov-Witten invariants are. So let's take a projective variety over C, and an integer, and a class in H2 that'll serve as a degree. And we're going to want to count. We're going to want to count curves on X of degree beta. And so we'll make a moduli space or stack of all of them. So let's let M bar GNX be a moduli stack that parameterizes maps from a curve C to X. Call that U. Think of C as being a curve on X. And then we've got marked points, P1 through Pn, that are going to be smooth points of C. And this G means that C will be a curve of genus G, will allow it to have nodes, and U has a finite automorphism group. And then we're interested in those curves that have fixed degree beta. And this moduli stack comes with an evaluation maps I for I 1 to n. And this will take the map U, P1 through Pn, and we'll map it to the image of U of Pi. So the Gromov-Witten invariant, NG x beta, takes input some classes in the cohomology of X, in the Li cohomology of X, and there's a virtual fundamental class of MGN bar, and so we can push forward the cohomology class, which is the pullback under the ith evaluation map of AI. So we take the cup product of all of these and then push it forward to the point, and this defines an integer, which then is a count of curves of genus G and degree B, passing through cycles representing the Poincare duals of AI. So we're counting curves subject to some conditions, like it runs into a line or a point, et cetera. So in the A1 land, we can define some of these. We can define the ones in genus 0 and on Del Pezzo surfaces, because these have nice moduli spaces, where the push forwards are something that we can define. And so what we can do is for an A1 connected Del Pezzo surface of degree greater than 4. In fact, you can do a little bit better than this, but for simplicity, so these are things like P2 and P2 blown up at less than or equal to 5 points, and they're twists. And then this beta is still the degree. It's like that class in H2. Think of it as the degree of a curve, like in algebraic geometry. And now we have point conditions. Before, in the previous slide, we were allowed to run through the Poincare duals of various cycles that we want, and now we're going to do points, but we're over a general field, or really a general field of characteristic not 2 or 3. So now running through a point, there are different kinds of points. The point might be an R point, it might be a complex conjugate pair of C points. So we're going to run our curves through points with residue field L1, L2, Ln. So if we want to know the genus 0 curves of degree B on X running through generally chosen points with those residue fields, it's possible to construct a number in, or an element of this growth and Witt group, this quadratic form, that's a well-defined count of such curves. So what this gives is that there is one conic, bracket 1, sorry, there's one line through 2 points on the plane if they're rational, or in fact, if they're a conjugate pair of any degree 2 extension. There's one conic through 5 points of the plane, and again, those that can actually be sort of 3 points that are in a conjugate pair for some L1 that's degree 3 over your ground field. So it might be 3 points that are really in one Galois orbit, and then two rational points. It doesn't matter what they are. For degree 3 curves on the plane, so degree 3 plane curves, you should run, so plane curves, they're, to make a map to P2, you've got 3 polynomials of degree D, so that's a D plus 1 times 3. But then you projectivize, you subtract 1, and the automorphisms of P3 has degree 3. So there, you want 3D minus 1 points to get a finite number of genus 0 plane curves of degree D. So we want 8 points. We want to run degree 3 genus 0 curves through 8 points of the plane. And now the answer now depends on which points you choose. So it's 2 times this diagonal form with 1 or minus 1, plus this term here, which depends on the fields of definition. This is the trace form of the field extension from Li over K. So if you choose all rational points, Sabrina Pauli and Andres Jaramillo Puentes compute the number of degree D curves on the plane, or degree beta, completely, or for any toric Del Pezzo. And the answer is that it's some integer A times 1 plus some integer B times minus 1. And you can tell what these are by taking the rank, which is A plus B, and that has to be the complex answer, which is known, and the signature, which is A minus B, which is the real answer, which is also known, and then that's the arithmetic answer as well. However, even for P2, the answer is unknown in general. The P2 itself is smooth and proper over Z, but since the points that you run through might not be rational, we can tell that they're not all of this form. Moreover, the surfaces and Del Pezzo surfaces are not the only class of algebraic varieties out there, and there should be A1 Gromov-Witten invariance, Gromov-Witten invariance with arithmetic information behind about half of the Gromov-Witten invariance for things like projective space or A1 connected. And they'll be in GW of K, and they're recording something about curves on varieties. Let's talk about some tools we can use to compute what that arithmetic information is, more than over R and C. So I'm going to talk about some joint work with Erwan Bruegele that gives some information about the A1 Gromov-Witten invariance. So first, actually, let's talk about surgery, which is something that we can do to a manifold. So surgery, you have a dn plus 1 times an sm here, and then you can replace it by an sn dm plus 1 by cutting along there and adding it back in. And so this happens with quadrics. So in P3, we have the zero locus of x squared minus y squared plus c squared plus w squared. That looks like this. This is a diagonal matrix when you express it as a quadratic form, and its determinant is minus 1. So let's just call this sigma minus 1. And similarly, if you draw the solutions to x squared minus y squared plus c squared minus w, you get this, which has discriminant plus 1. We could call that sigma 1, but let's just call it s. And between these two, there's the singular quadric like so. So you can take one del Pezzo and perform a kind of surgery if it comes from, if you have a family of del Pezzos that acquires a minus 2 curve, you can perform a kind of surgery that takes the S naught times D2 to the S1 times D1. So what is a family of del Pezzos acquiring a minus 2 curve? So a del Pezzo is a blow-up of P2 at some points, and then you can twist and get interesting arithmetic information when your field is not algebraically closed. Okay, so we're on a plane. We're going to blow up some points on a plane. Let's blow up 6 points on a plane. And 5 of those points are going to be on a conic, but all 6 are probably not. If, however, you degenerate into the position where those 6 points will be on a conic, then the strict transform of that conic will be a minus 2 curve. So you can blow down that minus 2 curve and get a node. And then if you pull back by changing a coordinate by d and then blow up, you can either get into this situation or get in this situation on either side. So there are a lot of families of del Pezzos where you can, for each d in the constants of your field, do a surgery and define a lot of different del Pezzo surfaces sigma d. And it's a result of deformation theory that when you want to count the genus 0 degree B curves on sigma d, they're in bijective correspondence with curves that are now reduced into a whole lot of components on a special fiber of this family, which is a del Pezzo S twiddle with a minus 2 curve E, plus the quadrics that we were looking at with varying discriminants. So D is going to be the discriminant of this quadric. So that's deformation theory. And so here's a picture of that. We're interested in genus 0 curves on this sigma d. It's just drawn as kind of a plane. And there's the curve there. And it's going to specialize in a unique way to a curve that breaks up into a bunch of pieces. And these are actually easier to count. So it's a curve C on this S twiddle, and then with a bunch of lines that are in one of two rulings on Q. So the summary is to count reducible, well, okay, so we're now going to count curves on this union of S and Q over E. We're going to do it by counting curves here, and then we'd like to choose some of these points of the intersection of C and E to make little orange tails on, and then the rest will make pink tails. So we'd like to choose, say, 2 out of 4 intersection points. So here, 1, 2, 3, 4 intersection points of C and E. And it turns out you want to choose some of them, here 2, to draw orange tails out of. But wait a minute, those 4 points, they're not actually just 4 C's. We're not over C, we're over some K. So these 4 points, they're actually a whole bunch of field extensions. So we're actually trying to choose something. We're going to try 2 out of some field extensions. So you can put all of your binomial coefficients into the Grothendieck-Witt group, and that is what naturally occurs. So if you'd like to see Pascal's triangle in Grothendieck-Witt, today is your lucky day. So you can define a whole combinatorics in the Grothendieck-Witt group of K. You need some twisted versions, and you need these binomial coefficients. So here's a field extension. And so Erwan-Brueggelet is joint work with this wall crossing formula. We're going to say that, and Erwan's name actually has two L's. And also Chungyao Chen is doing work on some other formulas for Gromov-Witten invariance, also involving combinatorics in the Grothendieck-Witt group. And so here, in a finite field, we've got a unique degree n extension. This U is a non-square in the finite field. And there are actually more U terms. They don't just all sit here. There's a closed formula for how that happens. Deasia Brody and Zoe Valentine did some nice work on this as well. And for the surgery case that we were talking about, that gives this theorem here that says that here we're back in this situation where we have a family of del Pezzos acquiring a -2 curve, E, and we have this surgery operation that I briefly described. We're going to let S be that one surgery where we're sort of putting in a quadratic form of discriminant 1, and D, we put in this quadratic form of discriminant D, and here are Gromov-Witten invariants, the N counting the number of rational curves of degree B on X through points. I left off the 0 because we don't actually have genus 1 or genus 2. But it's not because I don't think they're out there. And the points can be not only a number of points, but they also have fields of definition. So okay, so here's our Gromov-Witten invariant. And what you can show by counting the curves on that reduced, counting those reduced curves and adding up some binomial coefficients is that the Gromov-Witten invariance for the surgery is the one for the one surgery plus 2 minus 2D times the sum of these Gromov-Witten invariants on the one surgery in degree B minus JE. So to get this here, there's a huge, big, uncalculable expression involving curves on S twiddle. So the curves on S twiddle are very hard to control, and you wind up in your count needing, so you count these by counting these ones here. And so you get a whole lot of terms with Gromov-Witten invariants of S twiddle, which are utterly uncomputable because they depend on precisely where you choose your points. Like we have these Gromov-Witten invariants where if you run through 8 points, and those 8 points are in general position, you always get 12 curves over the complex numbers on the plane. And it's really useful that you can choose those 8 points generally, and you get the same number. And on S-twiddle, you don't have that, so you would be in hard luck to try to compute Gromov-Witten invariance for this from this. Now, that's what you're doing with this specialization, but luckily, everything cancels out. And so you get a big combinatorial formula with a lot of binomial coefficients and a lot of different field extensions that you couldn't possibly control. But they all cancel out, and they're always, no matter what the field extension is, they give you this little person right there. And so you get a usable equation where both sides are nice and invariant. And we can compute the Gromov-Witten invariance for this kind of surgery. I'd also like to point out that even if we start with P2 and rational points, where we had a lot of bracket 1s and a lot of bracket -1s, and that doesn't look very arithmetic. If the real story and the complex story are determining these things, it tells you something, but it doesn't. The real story and the complex story don't tell you the arithmetic Gromov-Witten invariance. When you've done something to your variety that has arithmetic content, you can't get rid of this 2D. You can prove that it's not a bunch of 1s and -1s because it has a residue at D. So applications you can do with this, you can run your points, not through rational points, but for degree 2 field extensions, and then compute them for P2 or toric or anything that you have the values for the degree 1 extensions. And this is also done tropically for toric varieties by Andreas Jaramillo Puentes. And this will also give all of them for quadrics. And let me just leave you with a bunch of examples. So if we take here's a quadric with discriminant D, and we take the degree, so this discriminant, this quadric over the algebraic closure looks like P1 cross P1. And so in the P1 cross P1, let's take the degree to be 2, 2. I know that's anti-canonical, because the cotangent space of P1 is O of -2. And so this is 2, 2. We can actually do them for 3, 3, 4, 4, or anything like that, which is the whole Picard group of this over K. So that's actually an accident. But in any event, so we have this quadric. This is one of the things we can do. It goes through minus ks dot b minus 1 points, so that's 7 points. Let's choose them all rational here. And here's the Gromov-Witten invariant. And note that there is this d here. And so this has a residue at all the prime factors of d. So it's just not a bunch of 1s and -1s. It also has a 2. And then here's a cubic surface. And we could run this through with, and let's do the anti-canonical class again. This is essential, but I don't know how to do it in general, but it's not essential here. And you run it through 5 rational points, and you do pick up a little 5. Okay. So there is some arithmetic information behind about half of the Gromov-Witten invariants out there on A1 connected schemes. Let's find out what it is. Thank you.